Hello guys, so welcome to channel Rowan Basic. So in this video we will learn about exponential functions. So on basic definition, an exponential function with base b is a function of the form f of x equals to b raised to x, or it can be in the form of y equals to b raised to x, where b is greater than 0 and b is not equal to 1, and x is any real number. So in some books, you can find another form of your exponential function as f of x equals to a b raised to x, or shall we say minus c in here plus d. Okay. So later I will discuss this form of your exponential function, but let us first go to the application of exponential functions on your real life. So we have exponential or population growth, exponential or population decay, and we have your natural exponential function. So I will give you some example later for the population growth, population decay, and the natural exponential function. Okay, so first let us discuss this population growth, then the population decay. So from your form, let's say let us use y, this form. Okay. Y equals to a b raised to x. So in application to population growth, you can find in your books such form as this one. A this one. We have y equals to a times the quantity of 1 plus r raised to x. So if you can see, b is equal to 1 plus r. So this quantity is known as your uh, factor, rate factor. And r is your rate of change. Okay, so we have to conceptualize that in population growth, we are dealing with problems and situation where one example population is from this point and increasingly or exponentially increasing, such as the population of bacteria, humans, and of course your money. Okay, so we have y equals to a times the quantity of 1 plus r raised to x. In application to your exponential or population decay, from the form y equals to a b raised to x, we have this one. So a times the quantity of 1 minus r raised to x. So population growth discusses about the increasing trend of your exponential function, while a population decay explains or can be applied on problems with relation to decreasing exponential functions or the decreasing trend. Okay? So we have that one. If you can see that the difference, this 1 plus r and 1 minus r as your change factor or the change rate factor. Okay? Then another one for the population decay is your half-life. So half-life is applied on radioactive substances. Okay? So it follows this equation or function. Y is equal to y sub 0 times 1/2 raised to p over t. Or in some cases, we can put this half-life formula into y equals a times 1/2. Then we have p over t as an exponent. Okay? So a, just like a and here, are your initial population. Okay, so later I will discuss it using examples. And let's go to your natural exponential function. So natural exponential function is always in the form of f of x equals to e raised to x, or shall we say y is equal to e raised to x. Okay, so let us discuss each application of your exponential function using examples. Okay, so let us proceed to our first example for your exponential function in application to population growth or exponential growth. So we have the situation: Mrs. Cruz invested 100,000 pesos in a company that offers 6% interest compounded annually. So define an exponential model for the situation, and how much will be the investment be worth at the end of 5 years. Okay, so let us start from the definition of your exponential function on your population growth. So we have y is equal to a b raised to x. And for your population growth, we have b is equal to 1 plus r as your growth factor. It would be your growth factor, because the trend of the money or population growth is, of course, increasing. Okay, so we will substitute b as a, then your growth factor is 1 plus r raised to x. Okay, so a is your initial value. R is the rate of change or the rate of growth for this situation. And the quantity of 1 plus r is your growth factor. But to make this short and simple and apply to this situation, you can see on some books the formula or equation for this is this one. Okay, so we have that one. A is equal to P times the quantity of 1 plus R raised to T. So they are the same. We just change the variables such as y for A, small letter a as your initial value, then you change it to P, then your rate factor, and then your x is for T. Okay? So using this situation, A, or the initial value, is your principal, the principal amount of the investment. So the principal is equal to 100,000. 100,000 pesos. Then the rate R is 6%, or we can change it in decimal as 0.06. 6% is, to change it to decimal, just divide 6 by 100, then you can get 0.06 or 6 hundredths. Okay? Then using the initial value and the rate, we can answer or define or write an exponential model. Okay? Okay. So additional information: A equals to P times the quantity of 1 plus R raised to T. In some books, you will find A is equal to F. F stands for the future value or the maturity value, because this problem deals with compounding or a compound interest. So let's just leave it and let us focus on A is equals to T times the quantity of 1 plus R raised to T in application to your population growth. So we will write or define an exponential model. So your PS, your initial value or your principal, is 100,000. So we will just have to disregard some of the units. 1. This, and your rate is 0.06 raised to T. Simplifying, we have 1.06 raised to T. Okay. So this one is the exponential model for this situation. So very easy. So the second question is, how much will be the investment after 5 years? So using your exponential model, we can easily solve the investment after 5 years or any year you want it. Okay? So let's try this at A is equal to 100,000 times 1.06 raised to, so we will add up our given. Our given is 5 years for your T. So compound it annually. So the exponent is T is 1. You substitute T for 5 years and compute using your calculators. So we have A is equal to 133,822.56. So at the end of 5 years, the 100,000 pesos will become 133,882 and 56 centavos estimatedly. So let's add up the unit of peso sign. Okay? So if you want to solve for the money after 10 years, just substitute 10 on your exponent. Okay? So very easy. So that is one example or application of an exponential function when it comes to an increasing trend, or shall we say your population growth. So now let's proceed to the next example for your population decay. Another example of an exponential function in relation to population decay is on the board. So the population of dolphins was 100,000 in the year 1980. Then every year the population decreased by 3% as a result of climate change and pollution. So we will write an exponential function for this situation and we will answer the question, what is the number of dolphins in the year 1990? So let us first define your exponential function for population decay. So we have y is equal to a, b raised to x, where b is equal to 1 minus r. So your growth factor is equal to b, or b equal to 1 minus r. If it is population growth, that will be 1 plus r on our first example. So this time b is equal to 1 minus r. Okay, continuing, we have y is equal to a, your initial population, times the quantity of 1 minus r raised to x. Okay? So your a is your initial population. Okay? Then r is the rate of decline or decrease. So in this situation, the rate of decline is 3% because we are on population decay. On population growth, of course, the rate of increase or the rate of growth. So let us write an exponential function for this situation. So your initial population A is equal to 100,000 and your rate of decline is 3%, or by decimal form we have 0.03. Okay? So continuing, we have derived your exponential function just like this form. So we have y is equal to your initial population is 100,000 times the growth factor. So the growth factor is decreasing in trend. So we have 1 minus r is 0.03 raised to your exponent x. Okay? Okay, simplifying, we have this function 100,000. 1 minus 0.03 is 0.97 raised to x. So this function is the exponential function for this situation. And we will be using this function in computing the number of dolphins or the population of dolphins in relation to x or time. Okay, so x will be the time. Okay, so let us answer the question, what is the number of dolphins in the year 1990? So from 1980 to 1990, so we have how many years? 10 years gap. Okay, so your t will be, or x will be 10 years. So we have to solve this here. Y is equal to 100,000 times the quantity of 0.97 raised to x, or 10 years. Okay? So using your calculators, you will get 73,742.412. This will be your value using your calculator, but we are dealing with the population of a certain species. So the correct answer will be y equals 73,743. Okay, so we can conclude that after 10 years, or at the year 1990, the number of dolphin will decrease from 100,000 to 73,743. So guys, we are rounding off your decimals when we are talking about a population of a certain species, like animals and humans. Okay? So at the end, or at the year 1990, the number of dolphins will decrease into 73,743. For next example of your exponential functions in relation to population decay, we have another example, and it is related to half-life. So half-life are focused on radioactive substance and the time it takes for half of the substance to decay. Okay, so suppose that the half-life of a certain radioactive substance is 10 days and there are 10 grams initially. So we have to determine the amount of the substance remaining after 30 days and give an exponential model for the amount of the remaining substance. So let us go to our basic form of exponential function. Y is equals to a b raised to x. So in dealing with half-life problem, we have the growth factor b is equal to 1/2 and x will become t over small letter t divided by capital T. Or substituting, we have y is equal to a for the initial value or the initial amount of the substance times the growth factor, which is 1/2. Okay, raised to x. So that will be your function. Or it can be simplified as y is equal to initial amount times 1/2 and x will become to small letter t over capital T. Okay, so you will understand it when we apply it to your problem. Or in some books you will find the half-life formula as y equals to y sub 0 for your a or initial value times the quantity of 1/2 raised to that one. Okay, so in case, just follow what you should follow. You can use this one or this one. So y sub 0 is the initial value, just like a. Okay, so let us apply. So your initial value a is 10 grams. Then times 1/2. Then your small letter t denotes the time. And your capital T is this one. Okay? That one. So this function, y equals to t times the quantity of 1/2 raised to t over 10, is the exponential model for the remaining substance. Okay? So this capital T is the half-life or the time where the substance will get its half-life. So every 10 days, the substance will decay or decrease its initial number into half. So assuming the substance is initially 10 grams. After 10 days, the substance will become 5 grams because it will decay by its half. Okay, so let us answer this question. After 30 days, what will be the number of the substance? or what will be the amount of the substance after 30 days. So we will just have to substitute y is equal to 10 times the quantity of 1/2 times, okay, so small letter t is 30 over 10. Simplifying, you will get 10 times the quantity of 1/2 raised to 30 over 10 is 3. Okay? So I guess we are clear in that. And after 30 days, we have y is equals to, using your calculator, we have 1/2 raised to 3 times 10. We will get 1.25 grams. So after 30 days, the substance will become 1.25 grams from 10 grams. Okay? So I guess we are clear on this.